Okay, I think we're recording. All right. Well, thanks everybody for tuning into this. This is the latest of the O1 Labs Twitter Spaces on applied use cases. We're actually recording this meeting in another medium because today it so happens that Twitter Spaces has been suspended. So recording elsewhere, and we'll publish the recording later. It's a shame we can't get audience participation today, but we want to just get this out there, so we'll proceed according to that plan. And the topic today, we thought it would be interesting to talk with Lucas from Snickerdoodle Labs. Snickerdoodle Labs is one of our launch partners, has been working with Snarky.js just to try it out and start working towards some plans for using ZKps in their project. I'll let Lucas introduce himself and the project after my introduction here. And then we're also joined by my colleague, Jack Servia, who's on the developer relations side. So yeah, we will move over to the main content there shortly. But I wanted to do a little bit of scene setting. So I'm Phil Kelly. I lead the business development work at O1 Labs. And we're running this series of Twitter Spaces to essentially try and get more of a conversation going in the market about applied use cases. If you have any suggestions for use cases you'd like to hear about next, or any feedback on how we're running all these sessions, then please feel free to DM us. And the reason that we're wanting to have these Twitter Spaces is that there's a lot of technical content out there in the market now, lots of ZK sessions that are pretty deep at conferences. Vitalik publishes papers on ZK a lot, but it kind of feels like the mainstream blockchain from 6 or 7 years ago, where people have realized that ZK is this incredible new power, and we're starting to be able to deploy it practically. It's coming into prime time, but the focus now needs to turn more to how we use it and where the breakout use cases are going to be. So that's why we want to talk about this a little bit more. And before we get into it, just a point about definitions of ZKPs, because it's a new landscape to a lot of people. And it's also a little bit confusing, partly because the news has been full of ZK layer 2s. So ZK or Snark-based layer 2s are amazing. And they use Snarks deep down at the protocol level in a way that's really powerful, but it's also a really, really narrow use case. And the builders and users so far are building and running, what you could pretty much describe as regular apps without zero knowledge in them at the application layer. So they're cheaper, faster L2s, which is great. But that's not the focus here. We're talking about using ZKPs that are in the smart contract layer. And the smart contracts run off-chain and therefore allow you to achieve things like privacy and attestation, because the only thing that goes on-chain is a proof of what happened off-chain. So the data that you're making a statement about, for example, it stays in the user's environment, the statement is proved, and then the proof is verified on-chain. So that's why, for example, it's pretty useful for identity. And that's where O1 Labs focus is. We've been working on an SDK that allows people to build and run off-chain smart contracts for verification and storage on the MENA blockchain. We use the SDK. We launched the SDK for that in June. It's called Snarky.js. There are not many SDKs out there currently for building and running off-chain ZK smart contracts. We think ours is really good for a number of reasons. Number one, it's built with TypeScript libraries. So our goal there was to make it accessible to developers who are not cryptographers, but want to build ZK smart contracts. And we think everybody should be starting to build ZK smart contracts. And so you can use TypeScript libraries. And when we say use TypeScript libraries, we mean it. We don't mean it's TypeScript-like or derived from TypeScript. It really does use those libraries. And that means that you can use some of the surrounding tooling, such as NPM natively. So there's a big ease of use and ecosystem point there. Also, it uses a version of Plonk that does not require trusted setup. So no ceremonies required, for example. That's pretty huge. It includes a module for recursion. That's a really powerful secret sauce. It's the basis of, for example, rollups and dApp-specific rollups. We're probably not going to talk about that a ton today. We probably ought to talk about it a lot more. And in particular, we've got unlimited recursion, so you can chain together a whole series of proofs and roll them up and keep the final proof a constant size for ease of verification. And then finally, we've got WASM in it in the back end, so it's optimized to run in a browser. And again, that's kind of important when you're doing identity, because it allows you to create a proof that your data's about your data that's in your personal environment without it leaving your browser. And then, as I said earlier, when a proof's generated using an app built using using Snugger.js, it's then sent to the MENA blockchain for verification and storage. We have been working, or the ecosystem's been working on QANet. We're in testnet now for that layer, and obviously moving towards full live ZK app layer, hopefully very soon. So it's exciting times. Okay, so back to the main topic for today, and I'm joined, as I said, by Lucas and by Jack, and I'll let you guys introduce yourselves. Jack, do you want to introduce yourself, and then we'll move to Lucas, who can both introduce himself and talk about what Snickerdoodle is doing.
Yeah, thanks so much, Phil. Hi, everybody. I'm Jack. I do developer relations at ON Labs, and I've been working with Lucas over the last couple of months to figure out what use cases Snickerdoodle might have for zero-knowledge proofs, and then to finally help build this proof of concept that we'll talk about today. And with that, I'll pass it on to Lucas.
Yeah. Hey, I'm an engineer here at Snickerdoodle Labs. As Jack just said, was working with Mina to talk about zero knowledge. At Snickerdoodle Labs, we're building a privacy-first protocol that enables data sharing with the real big focus of allowing individuals to own data and share that data and get the value out of sharing that data. And excited to talk about how zero knowledge can really improve that process.
Awesome. Yeah, and I know that there's kind of quite a lot that's still under wraps with Snickerdoodle. We know you guys have got an amazing background and are doing some really cool things. And I actually think there's lots of either unannounced or unrealized use cases for identity and credentials and people proving things about themselves in the web3 ecosystem. So we'll be looking with interest at the future announcements that you guys make. Anything you wanted to say about any other level of granularity about your interest in ZKPs, or do you want to move on to the particular scenario that you worked on?
I mean, for ZKPs, I mean, they're just really cool. Yeah. Right? There's a lot of stuff of, can I prove that I know something without revealing what I know? And that as a concept is fascinating. And I think a lot of people can see how powerful that is.
Yeah. And in the identity world, examples of that have been sort of pretty well talked about. Have been things like, what have I got in my wallet? Let me prove what I've got in a wallet without doxing my wallet. Let me prove activity that I've been engaging in Web3 without showing you all the details. So, is that the kind of stuff that's interesting to your project?
Oh yeah, to the project, like proving identity is really important, right? As you can't own a piece of data without having an identity that owns it. The big one I know we're going to be talking about today is data integrity, which is saying we know that this data is correct, and proving that we know this data is correct without revealing the data itself is really, really key.
Very cool. So do you want to move on to talking about the particular scenario that you worked on? And just for context, I know that we're probably going to be hopefully working together for a long time, and there's lots of exploration still to be done. So right now, this is very much just experiment and exploratory work with you guys. But I think it's kind of interesting to talk about the POC. Do you want to just tell us a little bit about the scenario?
Yeah, I'll jump into it. And before I go into the scenario itself, let me talk about what the first thing Snickerdoodle is trying to do, right? We're trying to help people collect and own their data and share it with people who are interested in the insights from that data. What this generally breaks down to is people will download a Snickerdoodle data wallet and collect the data about themselves. That data is only known by them. And so we have a bunch of different wallets that have data and need to send this data up to some central source. I guess they don't send the data up, they send insights from the data. Run an algorithm that says, hey, I'm Lucas. Instead of saying I live at this particular location, I'll say I live in the United States and I'm in this age range of 20 to 30, send it up to this central source. And so someone else can say, oh, I can get the value out of that data and we can maintain privacy and get insights from that. One problem with this approach, though, is that the data that is sent up to be analyzed, there's no way to verify right now if it's correct or not, right? I can say I'm Lucas, I'm from the United States, I'm a male, I'm 20 to 30. I could also say that I am a woman in Argentina who's age 60 to 70. right? There's no way to know which is correct. This is where zero knowledge proofs can come in to be really helpful. If we had a trusted data source, such as like a DMV that's publishing and signing data on the chain, right? We could solve the integrity problem by now getting that signed data that says, I am Lucas, I'm in the United States, signed by the DMV, and sending that up to the data aggregator. The problem is we've now kind of preserved integrity, but we haven't, it's not private. I'm sending my actual data itself up to the central service. Now this is where we can do some really cool stuff with zero knowledge proofs, which is I can make a proof at like the data wallet layer that says, hey, I can prove that this data came from a trusted source with the signature. I can now do an algorithm that says, hey, am I over 21? Return 1. Am I under 21? Return 0. And now I can send a proof up to the central server that has a proof that the data came from a trusted source, I'm over the age of 21, and that you can trust it.
Awesome. That's very clear. Thank you. Great explanation.
Yeah, I was gonna say, and so for the for this proof of concept, we just kind of built that, a very simple version of that was checking ether balance. You would check an indexer, the indexer would sign how much ether you had in your account, and you would return 1 if you had more than half ether or less, 0 if not.
Yeah, and is it okay if I just jump in really quick and
please
kind of explain like how all of these bits, fit together at like maybe like an architecture diagram level? So yeah, we have some sort of a block explorer or some kind of API that gets us information from the blockchain, and then this data is signed, and that can be done by any trusted party. Then the user themselves can actually query this data and store it in their Snickerdoodle data wallet where it never leaves their machine. And then when it comes time to prove something about it, they run Snarky.js on the local machine, inside of their browser, as a part of the Snickerdoodle data wallet, or as just like it could be in like a like a dashboard website that they access, and they get out basically the key information and a proof that they derive the key information from trusted piece of data, and also in a consistent way, that they checked that they were between the ages of 20 and 30 instead of the ages of 25 and 35. And so they send this proof and the meaningful data off to, then I believe it's called an insight platform, Lucas?
Yes, that's what we're calling it.
Yeah. And then people who are interested in this data have access to it, and they know that it's valid, but they don't know where it came from. And because the user is able to compute this proof, the output all on their local machine, they don't have to trust anybody else or reveal their information to anybody else.
That said really well, Jack. Thank you.
Yeah, but I just wanted to kind of like highlight where things run so that it, because I think that that's kind of where the magic in this happens.
100%. Yeah, the ability to run all of these insight algorithms locally, and not reveal the data to the central port is really a really important point to highlight.
Yeah. And actually, I meant to ask, do you sort of see any other maybe use cases or avenues where this pattern can be useful for Snickerdoodle, or even just like something that you think is personally interesting that this enables?
Yeah. Well, I mean, for the first thing is that we're using this example on a really like toy case right now, right? Like returning a Boolean. I think the first things that are fascinating is like, could you extend, like how extreme of an algorithm could you extend this to, right? If you can start doing some type of machine learning and verifying that you ran the correct algorithm on your data, that's really cool. Another interesting thing is I'm very curious on who is interested in this level of data integrity. Right now, we're not really sure, and it'll be really cool to see, hey, this person really cares that this data has been checked and this data comes from trusted sources. So I guess those are the two immediate things that kind of come to mind for, I guess, this flow.
Yeah. I think the answer to question 2 is you don't really know until you get these things into production. But I guess I have kind of a hunch that like crypto people tend to really like to try to break things. You can see this especially like in kind of the MEV world. And so I think it's pretty important that whatever protocols people are building are really robust against that kind of thing.
Yeah.
Yeah, and then kind of
throwing a question back.
Yeah, go
throwing
ahead.
a question back to you, Jack. So I guess when playing around with Snarky, a lot of it was kind of, it felt like building up some very simple classes.
Yeah.
Do you know how well running, like say I had a PiTorch model and I wanted
Yes.
to run this in Snarky and prove that I ran it?
Oh,
How well would that work?
Yeah, so this is an awesome question because this is actually something that I worked on about a year ago. And I won't dive too much into the details because it's kind of complicated. But in our program, really, we can do like multiplication and subtraction. We can do arithmetic very efficiently. And so that's not nearly as much of a problem as you would think. You can kind of, turn a machine learning model into a something that's provable without having a tremendous amount of overhead. The part that's difficult actually is in converting these, floating point numbers that, represent like the weights and the biases and the inputs for your machine learning model into these field elements, which are, the fundamental kind of type of all, zero knowledge proof systems. This is required by the underlying cryptography. And so you can, just sort of very naively represent these floating point numbers as, like a number of fields. You can find a way to construct a floating point representation from these field elements, but then it actually does become quite inefficient. You can imagine how much sort of legwork is required for each of these values that you're working with. And so the approach that people take today actually is to there's quite a few different ways you can do this, but they quantize their neural networks. And so what this means is that they take these parameters that sort of represent the state of the network, and they convert them from floating point numbers to discrete quantities, or like in this case integers that map nicely onto our finite field. And the reason that this is hard is because you actually can't train neural networks without very high precision. And the floating point numbers provide this and the field numbers don't. You can imagine jumping between like 1 and 2 for one of these values, causing just a massive change, like a huge ripple effect throughout the whole rest of the neural network. And so the approach that people actually use is I'll kind of explain like one which is called quantized aware training, which is where you kind of like this isn't exactly what's happening, but you basically train a neural network using floating point numbers, the same as you would normally, but you sort of round these numbers to discrete, quantities like 1, 2, 3, 4, 5. And so it happens is that then the numerical stability is there so that the network can actually like learn, but it ends up learning in such a way that all of the values for, the weights and biases and stuff end up being, like 1.000024 or, like 5.999996. And so then you can round this into the actual integers and have a network that works almost exactly the same. And then you can run this inferencing inside of a neural network. So sorry, that was even a little bit more long-winded than I had hoped. But
I mean that's really cool. So but to make sure I understand that, you're basically because floating points are really hard to deal with. You map the floating points into a field that's easy for ZK proofs to work. You train it in that dimension, that field.
And so
then you convert it from that field back.
Well, you train it using floating points, but you basically sort of, again, this isn't really what happens, but you kind of round the floating points in such a way that they imagine just like imposing a sine wave on every value, right? So that it's more likely to converge at 1 than it is at like 1, 2, 3, 4, 5. It's more likely to converge at all these values than it is at any other values. And so then it gets very close, and then and then you can just, as the final step, just sort of round these things to the actual discrete values like 1 or whatever, and then that maps perfectly into into our finite field. And so this is really powerful. It's obviously not as efficient as just running these like inferencing sort of steps directly on like normal physical hardware, but it's efficient enough that it's doable, and this opens the door to a lot of things that I think are kind of pretty cool. Like one of these things is like doing inferencing is a significant cost for a lot of people who have these kind of machine learning models in production. And so being able to move them to the edge or even to the client side, and then have the client basically do the work themselves, prove that they did it correctly, and then send back the result, I think opens the doors to some new kinds of applications that maybe would have been prohibitively expensive to build in the past, but it also gives you, access to, I guess, doing things that people would be uncomfortable with usually because of privacy concerns. So like, I can't think of a good example off the top of my head, but there's a lot of like machine learning models that would be really cool. Like they would provide me with really cool capabilities that nobody is going to be okay with sort of like running in a data center somewhere with some company having control of all their information. Like it's okay when Siri listens to me when I say, "Hey Siri." Oh no, I said, "Hey Siri." Sorry, but it's not okay if it listens to me all the time. Whereas if this stuff was running on the client side, I would be happy, for it to listen to me all the time. And I think that you could get really cool information out of that.
Yeah. And Jack, I was going to jump in and say that's super cool explanation. But as I say, with floating point numbers, we can actually, and we are dealing with some kind of quote unquote normal problems. You can work around them.
Yes.
But the issue is with highly complex calculations and routines. If you have to work around those many times in multiple layers, then it becomes difficult practically.
Yeah, that's a really good thing to highlight. This is purely a performance limitation. So we do have other data types that are composed of this field type, so that you can work with types that you're familiar with and build things that behave in ways that you would expect. But when we're talking about scaling this out to millions of operations, it becomes very inefficient to do this.
I think our next Twitter space is going to be somebody who's actually working with floating point numbers. So,
that's awesome.
Good stuff.
Oh, nice.
Yeah.
Cool.
Actually, well, to bring
sorry.
this back to the earlier, I guess the POC of you're running an algorithm locally with the zero knowledge proof and setting the results back up. You can imagine that model very easily lends itself to federated machine learning.
Yeah.
Right, where I send a model to a local device, to a data wallet. I have it train the model a little bit and send the training weights up.
Yep.
It sounds like it'd be possible to extend this to federated learning, right?
Yeah,
where I can train my model using ZK proofs to say, hey, I trained this model on trusted real data, and you can trust that I ran the right training steps.
Yep, exactly.
That's so cool.
Yeah, well, and so again, for reasons I won't get into, we're not sort of the only people that are working towards like sort of solutions for these kind of problems. Like PiTorch today has a number of sort of features built into it for like quantized neural networks, and so there's basically a lot of machine learning stuff is kind of like converging in this direction. And so we're kind of doing our part with the zero knowledge proof stuff, but there are other people who are building things that play nicely with this.
Cool.
Kind of vague, but yeah, just for the sake of time, you can go look at PiTorch's. Just Google PiTorch quantize, and you'll get a whole list of really interesting results that fit in really cool with this sort of vision of the future.
Excellent. So, do you guys want to move on and talk a little bit about your experience, Lucas, with working with Snarky.js and how you kind of got introduced to it and what your journey was through using it?
Yeah, I can jump to that a bit. So yeah, I was introduced to Snarky.js through you guys. Funny enough, that's why we're talking now. But Snickerdoodle and Mina had chatted, right? Because very clearly a zero knowledge is applicable to a company that's dealing with data and identity. And so we chatted to try to figure out like how we can make that work. So using Snarky, we actually had a slightly different use cases, but you highlighted, Phil, at the beginning of this, which is a lot of Snarky is built to extend a ZK contract, right? To put it up on the Mina blockchain, and the blockchain does the proof for you. At Snickerdoodle, we're hitting a very different type of problem, right? We don't necessarily want people's data to be on the blockchain because the blockchain is completely public. So we wanted to be able to run these proofs locally and then prove them off chain. Snarky did have a really good way to do that with the ZK program, and learning how to play with all of that was great. Again, shout out to Jack, who both was very helpful at answering questions I had, and also had built, along with other people at Mina, some really good tutorials. that were really helpful for just learning how this works. And it was pretty easy. Like, I can't emphasize how nice doing stuff in TypeScript is.
Yeah.
I didn't have to go down into Rust. I knew what the types were. I could jump into types, say, how does this work? So just kind of building this very basic example, I'd say took me somewhere between 10 and 15 hours to play with. And a lot of that was just learning and hitting that like one edge case. So building it was nice. It's also really easy. Like, we're talking a lot about, oh, you make the ZK proof. It was really easy as someone with a background in computer science to now make it a mental model of class. And right, when you're building something in Snarky, oftentimes you're building a class. I extend it. I say, oh, here are my fields. How I'm like, this is the ETH balance field. This is the trusted signer field. And now I have my function that says check ETH balance, and I give it the balance and the signatures. And so in a way, when working in Snarky, I decided to think of a zero knowledge proof as a class. And the class will prove that the functions ran in this order and the fields were these values. And that made it really easy as a developer to play with. I do have some complaints. Again, it's a new system. It's a new package, which means I can't just Google help. If you hit a weird error, you don't know why you're hitting that weird error. If a weird thing gets printed out in a log statement, you don't know why it gets printed out in a log statement. If some of the naming can be improved. Yeah. But overall, pretty smooth experience.
Very cool. And, one of the reasons that we had the launch partner program was to get feedback as we iterate through improvements. So yeah, we definitely appreciate the feedback on that.
Yeah, this is great. I also should highlight, I mean, yeah, we know that this is early days and stuff is still kind of in flux. And so even though you can't Google, a error message and get a perfect response, we do have things like office hours and a Discord channel on our, I think it's called ZKapps developers, that you can go to, and we have lots of engineers there all the time, so that hopefully, even if you can't Google the answer, you can talk to you can talk to somebody who will be able to find you the answer pretty quickly. That way, turnaround time is pretty short until you get to a point where things are, more mature and we have like answers on Stack Overflow and stuff. Actually, maybe I can also talk to you very briefly this idea of your programs sort of, your zero knowledge proofs being a class. And so this is exactly true for Mina smart contracts. And I'll kind of touch very briefly on what is the difference between ZK program, this part of the API that you used, versus a smart contract. So a ZK program is basically a function, and it takes in some inputs and it spits out some outputs, and it does some stuff in the middle, and then it proves that it did this stuff correctly. And so this is a super powerful feature because, as Lucas said, you can build solutions to problems that don't necessarily involve blockchains this way. You can just, take this proof and call a verify method on it. And if the proof is valid, then the verify method returns true, basically. And so you can, just build this into your existing kind of like Web2 project if you want to. But what you can also do with ZK programs is you can use recursive proofs. And so you can actually pass these proofs as inputs into other proofs, into other, ZK programs or other smart contracts. And so then this kind of brings to like, oh, sorry, go ahead, Lucas.
I would say, yeah, I wanted to highlight something that you kind of said that's really powerful there.
Yeah.
The recursive step. Mm-hmm. What can be really interesting, and again, imagine we were to extend this out in the Snickerdoodle context. I have my data wallet locally. I'm collecting my own data. I have this proof that says this data came from a trusted source, and I've run an algorithm. This is really nice because, one, this proof I can store locally. And so I can, of course, I don't have to recompute this every time. And two, if I have another algorithm that comes in, right, that says, I want to figure out, I can't think of a good example off the top of my head, but I can reuse that proof and run the new algorithm on top of that proof.
Yeah.
And so I don't have to keep generating all of these proofs from scratch. I can generate the first proof, store it. Another question comes in that I have to, like another algorithm I want to run comes in. I can feed that proof in, generate a new proof, which would dramatically improve computation because I don't have to keep computing this every time.
Yeah. And this even opens the door to like some really interesting things. Like suppose you have, some of this data, I don't know, I won't think through sort of what like the rest of the logistics for this would look like, but you could even have like a situation where people could have access to some of the data. Maybe the users could opt into it or something. And then people who built, machine learning models and were interested in, creating some sort of model and then maybe exchanging it for money or maybe charging like per inference or something. They can use this recursion to actually, run some kind of like, I guess, like insight generation model ad hoc, on the outputs of all these proofs. And then maybe prove that they've done this sufficiently well to like a customer without revealing their model. And then eventually, if the customer, decides that they want the model because it does what it says it does sufficiently well, then they could, pay the people who developed the model either per inference, or they could just buy the model outright.
Yeah. Well, actually, doing the machine learning example, I think a clean example of this is, right, I have my local data. Someone sends me the training step. I run a ZK proof that says, here's the results of my training step in a proof.
Yeah.
Someone then sends me back another algorithm that says, okay, now update your own local weights with this. And then I can use that previous proof to say, okay, this is what I sent in before. Okay, I build on top of it. Here's what my weights are now, and this is what you should update to next.
Yeah.
So like if you're doing this multi-step thing, it works really cleanly.
Yeah, and then there's also, of course, like a way to incentivize all of this.
Yeah. The other thing, Jack, you're talking about snarky. I think this might be something that like kind of seems obvious to you, is very deep in the weeds, but something I didn't realize and was makes this really helpful to build this POC. Is that the snarky proofs that you generate are just JSON blobs.
Yeah.
And so because they're JSON, it's just really easy for us. Again, we have a data wallet. We need to send this up to the Insight platform. We can just send a JSON blob up.
Yep.
Like there's nothing special we don't have to do. There's nothing magical. It's a JSON blob. It's easy to use.
Yeah. Yeah, exactly. And then you can pass this into a from JSON method and then call a verify method on that, and then that's it. That's how easy it is to verify the proof. So smart contracts are sort of like a superset of this. So we have this program that can prove that it ran correctly. And then smart contracts really are like, if ZK programs are functions that are provable, smart contracts are basically classes that are provable. And so they have some persistent information that would be stored on the state of the Mina blockchain, and they have maybe different methods, and then they have access to some other kind of stuff like the state of the world block height or whatever. But it's really that simple. Then you have this class and you call a method on it and you prove that you ran the method correctly, and you send the proof and the outputs, which could be like update to the chain state or some event that you want to emit or something like that, off to the Mina network. And if the proof is valid, then commits the state updates or emits the events or does whatever it's supposed to do. So like, yeah, I mean, you really built something that could run on Mina, and just it doesn't make sense for it to in this case. But the idea is kind of that it's basically you're doing the same thing whether you're building on-chain or off-chain use cases. And really what you're building is functions or classes, and it's kind of that simple.
Yeah.
Very cool. Jack, anything else we should discuss, or?
I'm not sure. I think one question I kind of had is, has this experience changed the way that you have thought about like computers or blockchains or even just like life in general?
Yeah.
You have kind of like a different sense for what the future holds. Like, what direction do you see things moving in?
So again, I think the first thing that was the biggest is just reframing ZK proofs in my mind. Again, it's one of those things that I've heard about. Basically, any web3 white paper has an obligatory ZK proof section. But this has been really nice for just framing what it is. Before, I thought it was I could run an algorithm and prove it, which is still kind of true. But again, working with classes, it's like much easier to be like, okay, I've defined these are the type of functions that I can run. These are the type of states I'm keeping track of. And that has been a really good mental model, both internally and to explain to other people, which is how it's it's working well if it helps other people learn.
Yeah.
It's also really interesting. Again, cryptography is just incredibly cool. And it's really nice to see like here's some stuff on the bleeding edge. It'll be definitely cool to see how this technology advances in the next 5 to 10 years, right? Because we can still tell that it is in its infancy. How it can be used, finding different use cases. Life in general is a pretty big one, but it's been pretty fun. I mean, especially working with you guys has been great.
Likewise.
So yeah, overall good time. And again, the big thing to just highlight it again is just a much better mental model of ZK proofs and how they can work. And again, I think what was interesting is this use case kind of sounds obvious in hindsight.
Yeah.
Right. You're collecting data locally. You want to prove something about this data, like prove that you ran this algorithm on the data and send it up to the server. Oh, use a ZK proof.
Yep.
That took us a couple weeks to figure out.
Yeah, exactly.
And
yeah, I mean, it's because it's so non-intuitive, right? It all sounds impossible, but then it's just possible.
Yeah. And so like it'll be really cool also to see when that kind of thing is more standard, right? Like similarly when I'm signing something to you saying like, hey, this data was signed by Lucas and encrypted by Lucas, like that's very intuitive to think about nowadays and like dealing with your keys. So it'll be fun when it becomes more intuitive to find the use cases for it.
Yeah, and I mean, I think it absolutely will. I think that like as soon as people just sort of realize what's possible and kind of, as you said, develop a mental model, I think zero-knowledge proofs will become ubiquitous very, very quickly, the same way that like, I don't know, elliptic curves or something like that has.
Very cool. Excellent. We'll probably wrap it up. So thanks again, Lucas, for your time today. And we're really excited to be teaming with Snickerdoodle Labs and look forward to continuing the conversation and the work.
Yeah, thank you so much.
Thanks, Jack and Phil. This is great. If anyone listening is interested, please check out snickerdoodle.com. We have a public and private beta coming up. You can join the waitlist for that. Check out our GitHub eventually. The protocol we're building to enable data sharing will be up there. And thanks, Phil and Jack. This was a bunch of fun. I learned a lot. I really appreciate all the time that you've given me.
Very cool. Thanks, Lucas.
It's been a pleasure working with you. Thanks so much.
Right. Take care then. Bye.
See you guys.
Bye all.